In this lecture, we're going to discuss digital filtering. We've talked previously in the class about analog filtering and how it's appropriate to use analog filters or design analog filters really in a pre-signal processing phase where we're trying to filter out noise or characteristics that we don't want present in our signal before we even begin to process it. Once we get to the part of the problem where we're actually going to do biomedical signal processing. We've acquired the signal, we have a data set, and now we want to take that data set and process it. At this point, most of the filtering that's done is digital filtering. And so while it's perfectly fine to analyze signals in frequency space using the fast Fourier transform or the discrete Fourier transform, when we talk about filtering, because we're actually talking about applying a filter transfer function to a signal, we often want to discuss that in the context of the Z transform and Z space. So the purpose of this lecture is not to provide a complete digital signal processing course or even an overview, but really just to familiarize you with some terminology if you've never seen the Z transform before. So to backtrack just a little bit, the Z transform is used in place of the Laplace transform. Typically a Laplace transform is used in two contexts. One context is if we have a system, a linear system, and we want to do a transfer function definition, often rather than doing that in terms of omega, which often means that our transfer functions have complex characteristics, we do that in terms of the variable s, where s is sigma plus j omega, and so our transfer function in continuous space becomes a function of s. So when we do the Laplace transform that's illustrated in this equation shown, we're actually getting a function of s, which technically is a function of sigma and j omega. And so the transform space is done into S space, and our transform, rather than being e to the j omega t, is e to the minus st. So we refer to S as a complex frequency. And the Laplace transform is also used in a number of other applications. It tends to give better representation of signals that are step functions, signals that have non-zero initial conditions, and some other times that we would prefer to use the Laplace transform. So because the Laplace transform is a transform that's taken in continuous space, when we go to discrete space, instead of the Laplace transform, we take the Z transform. So let's start with the Laplace transform equation. Basically, it's just a transform, and we almost always start our integral at 0 because the Laplace transform typically is a single-sided transform done only in the t greater than 0 space. So this would be our Laplace transform, and this variable of integration s is actually sigma plus j omega, where sigma is real and omega is an imaginary part. So sigma is often referred to as a damping term, and omega is the oscillatory term. Now, if we want to express that in discrete form as opposed to continuous form, we do this just like we've done in previous examples. The first thing is that the integral becomes a sum. And so rather than integrating over continuous space, we're now summing over discrete space. The variable t, which was a continuous variable in the integral, now becomes a discrete variable in n. And so in the e to the minus st term, we're going to replace s with sigma plus j omega, and we'll replace t with s, and the dt goes away because we now have a summation and not an integral. Now the first step in the Z transform is we're going to make a single replacement where this e to the minus sigma, the damping part of the exponential, we're going to make a replacement with r. So the e to the minus sigma n term is going to become r to the n. And then the next thing is, if you look now, we have this grouped r to the n e to the minus j omega n. So what we're going to do is we're going to define z, the variable z, or the variable z, to contain everything except n, which is our actual time variable. So we'll define z to be r e to the minus j omega, and sometimes that's written as absolute value of z e to the minus j omega, because r is simply the magnitude of that complex number that is z. So once we make that replacement, then we now have eliminated sigma and j omega from our sum, and everything is in terms of z. So the transform, rather than becoming a transform in sigma and omega, becomes a transform in z. And it is, once again, it is a summation, and in this example it is single-sided. So if we have some function x of n, then so we have some function x of n where we have x of n is just going to be an array of values, x sub 0, x sub 1, x sub 2, and so on. Then we can basically represent that in the z domain by taking the z transform using the previous equation. So coming back to the previous equation, we see that the z transform is just taken by taking the sum of each individual term multiplied by z raised to the negative power of whatever term we're in the sum. So if we have a little n number of terms in our function, then the z transform would basically have n plus 1 terms, starting with x sub 0 and ending with the last term. So one thing to note is that the higher negative powers in z actually are corresponding to elements from our data array x of n that occurred later in time. So really the z terms represent time shifted elements in our data array. So what I'm going to do is enlarge this a little bit so that we can see a little bit better. This slide is not coming out real well, so let me pause the recording here and we'll make these slides appear a little better.